Hey everyone, in this video we're going to be going over the Physics 103 Discussion 2B step-by-step solution to question number 6. Now I remember when I did this with my discussion group back in the day, it was quite the challenge, so it's definitely worth breaking down. Alright, so it states, we're part of a research team doing experiments on how certain biological processes in cells respond to zero-G conditions. We don't have enough money to launch a satellite or buy a ride to the space station. We're going to put our experiment in a rocket, launch it, then let it free fall. During a period between when the engine shut off and returned to the ground, the rocket payload will experience zero-G. So we've managed to locate a company that sells a rocket, and this rocket maintains an upward acceleration of 39.2 meters per second squared for 5 seconds, after which point the experiment will separate from the rocket and it will then be in free fall. So in order for our experiment to work, whatever that may be, our payload, which is usually the tip of the rocket that falls off, which has our experiment, will need to be in free fall for at least 1 minute. So the overarching question, should our team purchase this rocket? So we're going to skip this kind of step-by-step walkthrough and just kind of get right to it. So what's really happening is we're starting here with our rocket. We are going to shoot that rocket up into the sky. After a certain amount of distance, the payload, or the top of the rocket, is going to detach from the base. And that has a bunch of momentum because on this first rise, the rocket was accelerating. It detaches, and then this part of the rocket is going to keep moving from momentum, stop, and then finally free fall all the way back down. So the question's asking, will the rocket work based on its initial acceleration? And will it be in the air for more than 1 minute on the way back down? So let's break this into two parts. The first part is the initial acceleration, and then the second part is at this point when the payload detaches and it rises once more, and then finally loses momentum and begins to free fall. So that's rise number 2 and rise number 1. So let's work with the information that they gave us. We know our rocket from this company accelerates at 39.2 meters per second squared for 5 seconds. So that can be applied to the first rise. It's accelerating for 5 seconds as well. So I want to know, at this point here where it detaches, how far has it traveled? Let's go to our useful expressions and see if there's anything anything we could use to answer this. So we know that when the rocket's on the ground, it has an initial velocity of 0 meters per second. It's not moving. So it is moving, however, quite a bit when it gets to this point after 5 seconds. So what is that final velocity? That seems like a reasonable thing to try to solve. So what we can do is look, this equation looks good here for solving final velocity. We have time, 5 seconds, and we have the acceleration of the rocket. So let's apply it. We'll say that the final velocity is the initial velocity, which is 0 meters per second, plus the acceleration, 39.2 meters per second squared, times the 5 seconds that were in the air. And I want to point out, we're going to consider this acceleration, or any acceleration going in the up direction, as positive. So therefore, any acceleration in the negative direction, in the downward direction, we're going to consider that negative. Alright, so plugging in these numbers to solve for the final velocity, we know that that will equal 196 meters per second. So that's how fast this entire body is going, right at detachment point, which is here with the asterisks by it. So now we want to ask ourselves, how much, this thing has a lot of momentum. How much further will it rise in part 2? So we can think about now this VF as being equal to 196 meters per second. And if we're considering this to be the second rise, this is now the new initial velocity. So we're going to call this initial velocity 2, and at this point is the new final velocity 2. Now the thing about free falls, or any parabolic movement with projectile motion specifically, is if I have a block and I throw it, and it gets to the top and then it slowly starts coming back down, at the very tippy top it has an instantaneous velocity of 0 meters. So it's per second, and it's temporarily frozen. Same thing with this type of path. It stops and then it comes crashing down. So we know at the highest point possible, before it starts the free fall all the way back down to the ground, at this final velocity, we know that that's actually going to be 0 meters per second. So let's, given that we know the initial velocity for the second rise and the final velocity for the rise, we want to calculate the distance. So let's look to our formulas. This equation takes into account everything we need to solve for how much distance has elapsed in the second rise, and that is because of that variable x minus x naught. Okay, so how can we apply this? V squared, which is our final, which we can just write as 0, equals our initial velocity of the second rise, which is 196 meters squared, plus 2, what's our acceleration here? Well, after, it's no longer powered by the capsule because it detached, so the only acceleration affecting this payload, or our experiment, is actually gravity. And gravity is going to act in the downward direction, which we designated as negative. So we're going to write negative 9.8 meters per second squared times our distance, which I'm just going to write as d for distance. How far did it travel from the detachment point? So simplifying this, I'm going to leave off units just so it looks a little bit cleaner. We have minus 19.6 times d. So now we're going to add that to both sides. 196. And for the first distance, we get 19.6. Oh, quick correction here. I didn't remember to square that one. So 196 squared is going to be 3,800, or 38,416 divided by 19.6, and that's going to equal 1,960 meters, because we were working with meters per second. So going back to our picture, that means that this second rise was 1,960 meters. Okay, great. So we know how high it went from this point, but we still need to figure out the first rise. How high did it go until it detached? So we can actually use the same exact equation and plug in a different set of numbers. So I'll rewrite it down here. Plus 2a x minus x naught, which you can think of as just distance. So our v squared final is actually this final velocity here. So 196 meters per second squared equals, we said our initial velocity was 0 meters per second, equals 0 meters per second squared plus 2. Now what's our acceleration? This is where we incorporate the 39.2 meters per second, because in this first rise, we are still being powered by the capsule. So 39.2 meters per second squared times our distance, this variable up top. So doing a little bit of rearrangement, we know that 196 squared is 38,416. That's equal to 0 squared, which is 0, plus our 39.2 times 2, which is 78.4, multiplied by our distance. So solving for distance, we end up getting, divided by 78.4, we end up getting 490 meters. So that is our first rise, 490 meters. So what does that mean? If we add these two up, we get the total height that the rocket moved. So 1,960 plus our 490, and that gives us 2,450 meters. Okay, so let's redraw a simplified version of what we know. This rocket has accelerated up using the jet fuel. The cap detached. It kept moving. It lost momentum, and at a specific height, it began to free fall all the way back to Earth. And we found, if we say that the ground is 0 meters, we found that it moved a total height to 2,450 meters of elevation. Okay, so now we want to know how much time will elapse from this initial starting point all the way down to the ground, because if it's over a minute, then that's good. Our rocket is good to go. If it's under a minute, it will not work for our experiment. So how can we solve how much time elapsed from this fall off? Let's look back to our useful expressions. What incorporates acceleration and time? Well, that's when we can apply this middle equation right here. So I'll rewrite it. We know that x equals x naught plus v naught t plus 1/2 at squared. So let's plug in these variables. X and x naught. Well, if we're focused on the free fall, or essentially just this straight down path from the highest point, our initial position is going to be the 2,450 meters. And our final position is going to be rock bottom, the ground, which is 0 meters. So our initial velocity, remember when we said we have a parabolic arc, at an instantaneous point, its velocity is 0. It's frozen in time. So now we can actually just plug in 0, so that term cancels out, and we're left with 1/2 at squared. And again, it's moving in the downward direction. It's not driven by the capsule. Gravity is the driving force. Since it's in the down direction, it's negative. So multiplied by 9.8 meters per second squared, multiplied by time squared. So if we simplify this equation, solve for t, we will have our answer. So let's do that really quick. I'll leave out units so it looks a little more simple. So then 9.8, we're left with times 1/2. Oops. 9.8 divided, we are left with negative 4.9 times t squared. So let's move the 4.9 to the other side. 4.9 t squared, 2,450. Divide both sides by 4.9. 22,450 divided by 4.9. We have time squared equals 500. Take the square root of 500. And we are left with time being equal to 22.4 seconds. Now we know that a minute is 60 seconds, so our rocket fails. It does not work. So I hope that breakdown was helpful.